Alright, hello class. In this video we're going to be talking about change of variables for antiderivatives. And this is often called u-substitution. As we go forward, you'll hopefully see why we call it that. But this is essentially the backwards chain rule, right? And it's really the main rule that we're going to be focusing on in this particular class. You won't get a backwards product rule until Calculus 2 and other rules like that until later, but we will talk about the backwards chain rule, and that has a lot to do with the fact of how, say, important the chain rule is. Well, the need to reverse it is also really important. All right, so let's talk a little bit about how this works, and we'll do a bunch of examples. All right, so as we recall the chain rule, if we're taking the derivative with respect to x of f of u, where say u is some function of x, it comes out to be f prime of u, so f prime of the outside with the inside left alone, times u prime. Okay, so that is the basic idea of the chain rule. Now, if we were to reverse it, right, reverse for integration, what we could say is that the integral of f prime of u times u prime dx is equal to f of u plus c. Right? All we've done is swap these around. So this is the basis for change of variables or u-substitution. Right? Because what we're looking for is we're looking for some function of stuff, right? E to the stuff, stuff squared, whatever, and the derivative of the stuff sitting outside. We could also think of this as, say, we have the integral of some constant k times u prime times some function of u dx. Well, that, okay, we can also say that that's going to be, say, k times capital F of u plus c. Okay, so what we're essentially looking for is a function with stuff on the inside and a version of its derivative on the outside. It doesn't have to be the exact derivative, but a form of the derivative, or basically a constant multiple of the derivative. All right, so we can basically apply this u-substitution to situations, or this backwards chain rule, to situations where we have a function of some stuff with a constant multiple of the derivative of that stuff out front. Okay, so if we have an f of u and a u prime sitting outside. Okay, so I think the easiest way to describe how this works is really just through an example. Okay, so let's start with an example of how this would work. All right, so for the first example we'll look at, let's say we have the integral of 2x e to the x squared. So notice that we're looking at this piece here, and this is what we're looking for. This is an e to the stuff, right? And it's not just an e to the stuff. The derivative of the stuff is sitting here, right? The derivative with respect to x of the stuff in this case is right here. So that's 2x, right? So the stuff itself is x squared. The derivative of the stuff is 2x. All right, so the integral can be done using u-substitution. All right, and so I'm going to start abbreviating this as u-sub, so we can use a u-sub. Now, how does a u-sub work? Well, here's what we do. Okay, that stuff, right? We're going to take the stuff, right, and let u equal it. Okay, so we're going to let u equal x squared. So this is the stuff in the exponent in this case. Okay. And then, if u is equal to x squared, that means du by dx is equal to 2x. Now, what do we do from here? Well, this may seem a little odd, but what we're going to do is move this dx over, and that gives us that du is equal to 2x dx. So if we look back at our integral, this x squared we could rewrite as u, and then what's more, this 2x dx can be rewritten as du. Okay? In fact, if I rewrite the integral in this order, let's say it's e to the x squared times 2x dx. Maybe it's a little easier to see in this case that, well, the x squared would become u, and the 2x dx will become du. Right? So when we make this transformation, which is an x to u, and this is also why it's called change of variables, because if we translate this integral into u's, it then simplifies down to just being e to the u du. All right? And e to the u du, well, that integral is just e to the u plus c. And now we don't want to leave this in terms of u, so we're going to translate it back now from u's into x's. And to do that, well, now we just replace that u with the x squared. Okay, now I think a lot of you may have already guessed at what this answer should have been. It would just be e to the x squared plus c. And we can check that, because if we differentiate, say, e to the x squared plus c, by the chain rule, the derivative of e to the x squared is itself, then times the derivative of the exponent, which is 2x, and then plus 0, and that's exactly what we had up there. Okay, so the idea of u-substitution is this idea, is that we find u, find du, and make a transformation. Now, it's not always going to be as simple as this, that this 2x dx comes out to be exact. So let me show you some examples on how we approach situations like that. Okay, so the overall process for u-sub, let me write this out before we look at that next example, is one, we want to look for u, right? You're going to look for like e to the stuff, right? Or stuff to a power. Okay, or like a trig function of stuff. Okay, or like 1 over some stuff. Okay, you're basically looking for stuff within a function, and so you set u equal to the stuff. Okay, then to differentiate, right? We differentiate. Find du dx, which would be stuff prime, to finish the transformation. Okay, and then we transform. So now we transform from x into u. So what's going to end up happening is you'll have like a constant k times u prime times f of u dx, and you're basically turning this into maybe just some other constant, say s f of u du. Right, so it's, as you can see, it's simplifying our integral down to something a lot easier to deal with, so that then it comes out to just be s times capital F of u plus c. And the idea is that this would end up being a much simpler integral to deal with, right? And then put your x's back in. That will be the last step, is plug the x's back in. All right, so as our next example, we'll have the integral of x to the 4th all times x to the 5th plus 6 all raised to the 9th. So here, this is a situation where we have stuff raised to the 9th, right? So here's stuff, and it's being raised to the 9th power. And the derivative of the stuff is almost sitting right here, right? So this is equivalent to stuff prime. Okay, so we could set up a u-substitution here. All right, so let's do that. Let's let u be this stuff here, x to the 5th plus 6. All right, then du over dx, right, the derivative of this will be 5x to the 4th. So something to note here is that we don't have the exact derivative in our integral. We have something close, right? We're off by about 5. But that's okay. Let me show you what you do in cases like this. All right? I have du by dx is equal to 5x to the 4th. I'm going to move the dx over here and everything else over here. Now, if you've been taught this material before, this may not be what you were taught to do, okay? But it's going to work, and I'll show you how. So I'm going to move the dx over, and this whole thing over here. I'm basically doing a swap, right? So I'm going to have let me clean this up a little bit. I'm going to have du over 5x to the 4th is equal to dx. Now, what has this done? Well, what this has done is basically I can replace this whole dx here with this thing here, right? I can do a one-to-one replacement because I've solved for dx, and maybe that's just what I should have said here, was solve for dx, because that's what we want to say plug in here. So while this thing is going to become u, this dx is going to become du all over 5 times x to the 4th. And when we plug that in, this x to the 4th will cancel with this x to the 4th. So when I was first taught this, I was taught to manipulate this thing here, over here, to move the dx over and manipulate it so that I had exactly x to the 4th dx. But it's not necessary. You can literally just solve for dx and plug it in and then cancel out whatever you get. So now we'll do our transformation from x into u. All right, so for the moment, I'm going to leave this x to the 4th here. And then this x to the 5th plus 6, I'm going to replace with a u. Raise it to the 9th. And then this dx, I'm going to replace with du over 5x to the 4th. And here, the x to the 4ths cancel. Okay? Now, here is your, I'm going to even draw it. Here's your red flag step. Right? If these things don't cancel, you've done something wrong, or you can't use u-substitution. Right? So that is your red flag step. We have no red flags right now because I can actually rewrite this now as the integral of, I'm going to move this 1/5 here, 1/5 u to the 9th du. If all the x's cancel out because you replace these x's with a u, and then when you make your transformation, if these x's don't cancel, you're in trouble. But here, all of our x's canceled out, and we can proceed as normal. Now we'll just integrate, right? The 1/5 comes along for the ride. The integral of u to the 9th will be 1/10 times x to the 10th plus c. And I totally messed that up. It's u to the 10th, right? So we will have 1/50 u to the 10th plus c. And now all we need to do is translate back from u's into x's. Right, so I have 1/50. Our u was x to the 5th plus 6. So I have x to the 5th plus 6, whole thing raised to the 10th, plus c, and that is our final answer. All right, if we wanted to double check this real fast and differentiate it, okay, the 1/5 would, or the 1/50th would come along for the ride, and we would apply the chain rule. We'd move the 10 down, leave the inside alone, raise it to the 9th, then multiply by the derivative of the inside, which would be 5x to the 4th, and the derivative of the plus c would be plus 0. So this 5 and 10 make a 50, so it cancels with this 50, and we will be left with x to the 5th plus 6 raised to the 9th, all times x to the 4th, and that's exactly what we started with here. Okay, so thankfully this method does work. However, you have to have this thing here where either the derivative of the stuff is sitting outside or almost the derivative of the stuff is sitting outside. So here we were missing a 5 to get the exact derivative, but you'll notice that that 5 came along right here as a 1/5, right? So, all right, let's look at some more examples. All right, for our next example, let's take a look here. We have the integral of sine cubed of x times cosine of x dx. So, again, we're always on the lookout for what our stuff is going to be. And if I rewrite this as we've talked about before, as this is being sine of x all cubed times cosine of x, then hopefully it's not too much of a stretch to say that we have stuff cubed, right? And our stuff here is sine of x. Okay, so here's our stuff, right? All right, so we're going to let u be sine of x. Then du over dx is cosine of x. So if you move the dx over, and often this is actually how I write this when I'm doing these problems. Instead of saying du over dx, I often just say if u is equal to sine x, then du is equal to cosine x dx. Okay, this is what's called a differential. So a derivative is when you have du over dx, but this is a differential. Du is equal to cosine x dx differential. Okay. We don't have to do much work here for a transformation, right? Because we have just the cosine x dx lining up exactly. Okay, so this thing right here will be our du, and we'll have u cubed when it's all said and done. Okay, so we'll make our transformation x into u to get down to the integral of what's essentially u raised to the 3rd du. So look at how much nicer this integral is. Okay, it's essentially just a power rule, right? It's the integral of u cubed du, and that's the whole idea here, is that you want an easier integral once you get down to it. All right, so if we were to integrate this now, we'd have 1/4 u to the 4th plus c, and then we just put our x's back in, go from u to x. So I have 1/4, and our u was sine. So we could say that that's sine of x all to the 4th plus c. Or if we wanted to match the notation that the book would give, it's 1/4 sine to the 4th x plus c. And there is our final answer. All right, I always liken this to, say, translating, right? If you speak, let's say, French as a second language, not as your first language, but as a second language, it's likely when you hear some French, in your brain, you translate it into English, process it. Say if someone asks you a question in French, you process it, get an answer in French, you translate it into English, process it, get your answer in English, then you translate it into French before you send the answer back to your French-speaking friend. Right? This is a similar idea. We got an integral in x that we don't really like, so we translate it into u. The u we do like, we integrate, and then we translate back into x. All right, so let's say we have the integral of 2x squared all over the square root of 1 minus 4x cubed. So my first thought is that the square root of the stuff should be where my u will end up being, right? So here's my first thought, that this would be our u, okay? So I'm just going to give it a try. I'm going to let u be 1 minus 4x cubed, right? And that means that du is going to be, when we differentiate this, negative 12x squared. All right? So, and with a dx, okay? Now, I'm just going to divide this over completely. We do have an x squared, right? So I'll just divide this over completely, get du over negative 12x squared is equal to dx, and just replace the dx with this expression here. Right? This is not necessarily the traditional way to do it, but I think it's a much quicker way to go about it. You can think less about what you're doing, just divide it directly. Okay, so now when we make our transformation of 2x squared over the square root of u, right, and then my dx will become du over negative 12x squared, and now we just cancel, right? These x squareds cancel, and this 2 will cancel with the 12 and leave us 6. The negative is still 6 around, so our new integral now is going to be the integral of negative 1/6 times 1 over square root u du. Okay, so what you're looking for is those x squareds to cancel. All right, now let's rewrite this in this way. I have negative 1/6 times u to the negative 1/2 du. That's one way to do it. There are a lot of ways we could approach this one, but I think just the power rule is good enough. All right, so the negative 1/6 will come along for the ride. Then the integral of u to the 1/2, well, that's going to be, u to the negative 1/2. When we add 1, we'll get 1/2. And then when we multiply it by the reciprocal, we'll get 2 over 1. And we have some more cancellations, right? The 2 cancels with the 6 and leaves a 3. And so we'll get negative 1/3. And I'm going to go ahead and put the u's back in. 1 minus 4x cubed all to the 1/2 plus c. And if we really wanted to, we could rewrite this as negative 1/3 times the square root of 1 minus 4x cubed plus c. Okay, either of these is fine. Okay, so I also want to mention finding the u, I think, is the toughest part of this. Once you find u, you're basically there. You then find the derivative and make a transformation. As long as everything cancels, you should be right on your way to getting the right answer. if you start getting like stuff that just doesn't make sense or doesn't cancel, go back and pick a different u. There's not a lot of stuff to pick as u in these problems, right? You only have maybe 3 or 4 choices, and if u substitution is going to work, one of those will work. Okay, now if u substitution is not possible, that's a whole different story, but you shouldn't see things like that until you get to Calculus 2. All right? All right, so for our next example, well, the integral of the square root of x plus 1 all raised to the 4 all over 2 square root of x. All right, so my first idea here is that the square root of x plus 1 should be our u, since that's our stuff to the 4th. Right, I'm thinking we have stuff to the 4th. All right, stuff to the 4th, so I'm going to let u be that stuff, which is the square root of x plus 1. Okay, so then du will be the derivative of this, so the derivative of root x will be 1 over 2 root x dx. Now, some of you might see that this automatically replaces this, because this is technically a 1 over 2 root 2 dx. So this already just gets replaced by the du. But even if you didn't see that, let's say you didn't see that, once again, you can just solve for the dx. So you would move this over to get 2 root x du is equal to dx, and then you can just replace it indirectly, and then you'll still get the cancellations you need, right? Because when we make our transformation, this root x plus 1 becomes our u to the 4th, right? We'll leave this 2 root x, but then our dx becomes square root, or 2 square root of x du, and these 2 square root of x's simply cancel. All right, and so now we're left with the integral of u to the 4th du. Isn't that much nicer looking than what we had here? All right, so the integral of u to the 4th is, of course, 1/5 u to the 5th plus c, and then we just translate our x's back in so that we have 1/5 times root x plus 1 all to the 5th plus c. Now, what I'll note is that I do understand that some people can do these things in their head, think backwards really well in their head. I do want to mention, for those of you, say, in a face-to-face calculus class using these lectures, that for any in-class assignments, I do want to see the u, the du, the new integral. All right, I want to see that you know the process. Even if you can, just think backwards and get the answer in your head. There are some integrals out there that you will need to know this process. Even if you're really good at thinking backwards, there are cases where a u substitution, an actual substitution, is required, and it's not something you could just think of in your head like that. Okay, we'll look at an example like that in this lesson, but they might not come up that often in this class, but in later classes definitely. So that is something that I am a bit of a stickler for in the face-to-face classes, just making sure that you know how to use this method when necessary. All right, complicating things a little bit here. Let's say we have the integral of 6x squared times 4 to the x cubed. Okay, so here we have, when I'm looking for something with stuff in it, this looks like a 4 to the stuff, which is a little different than e to the stuff, just by a little bit. Okay, so I'm going to let my u be this exponent, which is x cubed. Now, we should be pretty confident we're on the right track because the derivative of x cubed is 3x squared, and we have an x squared right there. Okay, so that is always a good sign that you're on the right track if you see something really close to the derivative already sitting here. Okay, so then our du is going to be 3x squared dx. Okay, and we can just go ahead and divide this through to get that du over 3x squared is equal to dx. Okay, so we'll replace this with a u, and then this dx will be replaced with du over 3x squared. Okay, so our new integral, I'll leave this 6x squared alone, and then we'll have 4 raised to the u, okay, then times du over 3x squared. And the x squareds cancel, and the 3 cancels with the 6, leaving a 2. So we're down to the integral of 2 times 4 to the u du. Okay, so the integral of 4 to the u, well, first of all, the 2 just comes along for the ride. The integral of 4 to the u is itself, then we divide by the natural log of 4. And then plus c. Okay, and once we put our x's back in, I say we just leave it like this. This will be 2 times 4 to the x cubed all over the natural log of 4 plus c. And there we go. All right, let's make things a little less complicated for this particular example. Let's say we have x to the 5th times sine of x to the 6th. So this is definitely sine of stuff. So I'm going to let u be x to the 6th, which means that du is going to be 6x to the 5th times dx. Okay, so we do have the x to the 5th, but we don't have the 6. So we can just divide by all this stuff, and so our dx becomes du over 6x to the 5th. All right, so when we make our transformation, I'll leave the x to the 5th alone. We'll get sine of u. Okay, then our dx becomes du over 6x to the 5th, and the x to the 5ths cancel, which is exactly what we want. All right, so then we end up with 1/6 sine u du. I'll leave the parentheses there for, I guess, consistency's sake. All right, and now we just integrate. The 1/6 comes along for the ride. The integral of sine of u, remember, is going to be negative cosine of u. That's something that's very easy to get mixed up. And then we just put our x's back in. So we get negative 1/6 cosine of x to the 6th plus c, and there we go. All right, so for our next example, let's say we have sine of x all over 5 plus cosine of x. Now, here's one of those examples where it can kind of be tricky of what our u is going to be, because we don't have sine of stuff. We don't have cosine of stuff. I mean, our stuff would be x, but that's not what I mean by sine or cosine of stuff. We don't have our sines or cosines to powers. Okay, so the trick here, whenever you have a fraction and you can't find anything else, right? You can't find anything raised to a power, this stuff is going to be your denominator. Because we can think of this as the integral of sine of x times 5 plus cosine of x all to the negative 1 power dx. So technically we do have stuff to a power. It's just our denominator. All right? So that can be kind of tricky. I do understand that. And I can relate to that. But yeah, if you're all out of options and you have a fraction, the u is probably your denominator. If it's not obvious what it might be, right? You don't have an obvious power, it's probably the denominator. Okay, so in this case, we will let u, right, be the denominator. So we'll let u be 5 plus cosine x, and that makes du equal to, well, the 5 goes away, derivative of cosine is negative sine of x dx. Okay, and we almost have that. We have sine x dx. Okay, so I'll just move this over to get du over negative sine x is dx. Right, so that's what we will put into our dx. All right, so we'll get the integral of sine of x all over u, okay, times negative du over sine of x. So we should be careful with what we're doing there. And look at that, the sine x's cancel, and we are left with this integral here, which is negative 1 over u du. Now 1 over u, that's natural log. All right, so in cases like this, when your denominator is the u, you're going to get a natural log pop up. Right, so this will be negative natural log absolute value of u plus c, which will be negative natural log absolute value. We're just going to put the u's back in, 5 plus cosine x plus c. All right, and there we go. There's our final answer. All right, for our next example, let's say we have x times secant of x squared times tangent of x squared dx. And how we approach this one is, you might notice, well, we have two things with stuff in them, but remember, our integral rule in this case is a secant x tangent x. So we're going to be looking for a secant u tangent u. So our stuff here is actually the x squared. Right? We have secant of stuff, tangent of stuff. So we're going to let u be x squared so that du is 2x dx. Okay, and if you divide, you'll get du over 2x is equal to dx, and so that's what we'll put in for our dx. All right, so we will get, I'll leave the x here, it'll be secant of u, tangent of u. Right, then our dx will become du over 2x, and the x's cancel. All right, so that means we will have, I'm going to move the 2 over, 1/2 secant u, tangent u. And that is one of our integral rules. That is going to be secant u. Because the derivative of secant is secant tangent, so the integral of secant tangent is just secant. And so here we have 1/2 secant u plus c. You put our x's back in, and we've got it. Okay, here's our final answer. All right, so be on the lookout. If you see secant tangent or cosecant cotangent, that's how this is going to work. You're going to be replacing u in two places. Okay. It's not the only time we'll see things like that. All right, so for example, here, if we have the integral of sine to the 5th x plus sine cubed x plus sine of x all times cosine x dx, our stuff, we have stuff to the 5th, stuff cubed, stuff to the 1, and it's all the same stuff. Right, we have the sine of x to the 5th, we have sine of x cubed, and we have sine of x, well, in this case to the 1. So it looks like we're going to want u to be sine of x. And when we do that, du, if u is sine of x, du is cosine of x dx. And that's exactly what we have right here. Right? So this will just become our du. All right, so this is actually going to come out to be u to the 5th plus u cubed plus u du. Okay, this whole thing came out to be du, and this is just a series of power rules. Right, the integral of u to the 5th is 1/6 u to the 6th. Integral of u cubed is 1/4 u to the 4th. And the integral of u is just 1/2 u squared. Throw in a plus c. And now all we need to do is put our x's back in. So our u was sine, so u to the 6th, we'll get 1/6 sine to the 6th x plus 1/4 sine to the 4th x plus 1/2 sine squared x plus c. Okay, so keep in mind you may be putting c's in, or not c's, but u's in multiple places, provided they all have the same sort of derivative sitting outside. All right, so for our next example, let's look at the integral of 8x plus 6 all over 2x squared plus 3x. And this is another one of those cases where I don't see the stuff automatically, and it's going to be where our denominator is the stuff, right? Because this is 8x plus 6 times 2x squared plus 3x all to the -1. So we can think of this as our stuff, right? This 2x squared plus 3x. So if we let u, okay, be 2x squared plus 3x, and no, we don't have to use this version of it. We can just use this version of it instead. All right, so anyway, letting u be 2x squared plus 3x, du is going to be 4x plus 3, and that whole thing times dx, okay? And so I'll just move that whole thing into the denominator. So du over 4x plus 3 is equal to dx, okay? And so this we will replace our dx with. All right, so when we get our new integral, have 8x plus 6 up top, u in the denominator, and then dx will become du over 4x plus 3. And let me make this a little easier to read here. Let's go around that way. Okay. Now, you might not think that this cancels immediately, but if we were to factor a 2 out of the numerator, right, this 8x plus 6, if I factored out a 2, we would have a 4x plus 3, and there we go, the 4x plus 3's cancel, and we're left with 2 over u du, and this will be a natural log. Right, you could actually move that 2 all the way out here and get the integral of 2 times 1 over u, so this will be 2 natural log absolute value of u plus c. All right, and now we just put that u back in to get 2 natural log absolute value of 2x squared plus 3x plus c. Now, I will mention that this is the final answer and this is fine. However, you may see, if you checked your answer in the back of the book or something, you may see this, natural log 2x squared plus 3x squared plus c. And all they've done here is move the 2 up to square it, and then you can drop the absolute value bars because you're squaring it. That's the same thing as making it positive, right? Absolute value squared is just squared, basically. But anyway, you don't have to do that, okay? Okay, so here's a great example of one that would be fairly difficult to do in your head. Maybe not, right? Maybe not. But notice we have 2 stuff things that we could look at. We have sine of 2x, that's sort of sine of stuff, and we have e to the sine squared x. So this is actually what I'm going to think of as my u, right? E to the stuff is a really good candidate for u substitution. Okay, so I'm going to let u be sine squared of x. Okay, and that makes du equal to, well, we need to do a chain rule here. So this will be 2 times sine of x times the derivative cosine of x dx. Okay, now if we just move this over to get du over 2 sine x cosine x is equal to dx, and do our transformation as usual, okay, we'll get the integral of e to the u times the sine of 2x right, and then the dx will be replaced by du over 2 sine x cosine x. Now you might think, well, hang on, this isn't going to work, right? Because sine of 2x is not going to cancel with 2 sine x cosine x. However, it actually will. It's maybe an identity that we don't remember, but we have this trig identity here that says that sine of 2x is actually equal to 2 sine x cosine x. So this is actually equal to sine of 2x. All right, so let me write that down in a new step. We have e to the u times sine of 2x times du over sine of 2x. So they actually do cancel. So this ends up being just e to the u du, which will be always my favorite integral or derivative is e to the u. And then we can just put the x's back in to get e to the sine squared of x plus c. Right, there we go. All right, so for our next example, let's look at the integral of the natural log of x over x. And this one is actually fairly tricky because it doesn't look like we have any stuff, right? We have natural log of stuff, we have x, and I'll give you some advice. If you ever set up a u-substitution as u equals x, stop right there. You're not doing anything, right? Because if you set up u as x, du is dx, and all you're doing is rewriting all the x's as u's, you actually haven't simplified the problem at all. So never think that u equals x is a good idea. Okay, that's never what you want to do. Okay, now, so we have ln of x over x. It may seem a little strange of how this is going to work, but I'm going to let u be the numerator. Okay, because I can't let u be the denominator, but if I let u be the numerator, right, I get u is equal to ln of x, and du is 1 over x dx, and that is exactly what we have right here. Right, this is the 1 over x dx. Okay, so this is one of those tricky ones where it's not exactly like stuff squared or, you know, anything like that. It's just sitting pretty all by itself. And I guess technically you could think of this as natural log of x to the 1. But even if you didn't see that here, that this is exact, you could still move this over as x du is equal to dx. Okay, so when we set up our new integral, the numerator will become u. So we'll have u over x, then times our dx becomes x du, and our x's cancel, and we're left with the integral of u du. And this will just be 1/2 u squared plus c. And now we can just put the x's back in to get 1/2 natural log of x squared plus c. And there we go. There's our answer. Now, I'll leave it up to you if you want to check to see if that gets us back to where we started. But yeah, be on the lookout for some weird things like this. There's a lot of weirdness that can come up with u-substitutions that you might not anticipate. For example, let's say we have sine of x times secant to the 8th of x. You might think, oh, there's our stuff, right? It's secant to the 8th. So it's right there. I'm going to let u be secant of x, right? Then du, and here's where we'll start to get into some weirdness. Du will be secant x tangent x dx. Okay, and so then if we were to move this back over, we'd get du over secant x tangent x is equal to dx. And we would get now the integral of sine x times u to the 8th times du over secant x tangent x. And that does look kind of gross, doesn't it? Right? That does look kind of gross. However, let's see if we can play with it a little bit, right? Because secant is 1 over cosine, so 1 over secant should be cosine, right? So we'll have sine of x, u to the 8, and then this 1 over secant becomes cosine of x. And this tangent is sine over cosine, so it's going to become cosine x over sine of x. So the sines will cancel, but we're now left with cosine squared. So this is not actually the way we probably want to do this, right? So what do we do instead? Well, instead, what we should have thought about was the fact that we need the form of the derivative of what we're letting u be to sit out here. Derivative of secant is secant tangent. Sine does not satisfy that. However, secant is 1 over cosine. So we could instead rewrite our integral as the integral of sine, right, times 1 over cosine raised to the 8 of x dx. And this is what we'll let our u be, right? U is going to be cosine of x, so that du is negative sine x dx. And there we go. That should get it to us, because we'll have du over negative sine of x is dx, and that we can put into our dx and actually get a cancellation, right? So when we do our transformation now, we get the integral of sine of x times 1 over u to the 8th, and then dx becomes du over negative sine of x, and then the signs cancel, and then I'm going to rewrite this as an exponent so that we have the integral of u to the negative 8 du. And there we go, right? We'll add 1, so we get u to the negative 7 divided by, oh, and we have a negative, sorry. That negative should come out. So let me do this again. We'll have a negative, then a negative u to the negative 7 over negative 7, okay, plus c. So it comes out to be 1/7. Then u, of course, was cosine, so this will be cosine x to the negative 7 plus c. So we could leave it like this, We can move the cosine into the denominator. We could change it to be back to secant again. All right, there's a lot of ways we could go about it. The important part isn't that here, is getting to here. All right, so I think that is definitely enough for this particular lesson. Once again, I say this a lot, but there are way more examples and types of examples that I could ever do for you. But hopefully this takes care of a big swath of the types of things that you will see. All right, so as always, if you have questions, let me know, and I will catch you all in the next one. Cheers.